Our next speaker is Marzena Rostek. She will be speaking about decentralized market design. Marzena, the screen is yours.
Thank you to Marina and Naveen for organizing this conference, and thank you for having me. This talk is based on papers joined with Ji-Hyun, who is also here and will peek at the Q&A. These papers all grew out of thinking about the realities of financial markets, which are at odds with a couple of assumptions in the classical equilibrium theory. Namely, the assumption that financial markets are perfectly competitive, that is, no individual trader has impact on prices, and that trading is centralized. Essentially, a single aggregation, a single market clearing applies to all traders and all assets. It's been well understood, at least since the late 80s, when individual trade level data became available, that financial markets are dominated by large institutional investors who do have price impact routinely estimated and take it into account when trading. A bit more recently, the financial crisis of 2008 highlighted the extent to which trading is centralized or decentralized or fragmented. Essentially, all financial assets are traded in multiple coexisting exchanges and trading venues of various kinds, often for the same traders, often for the same assets. This is the case not only for assets with units as heterogeneous as real estate, but also for assets with homogeneous units. We have a rich theory of design for centralized markets, for organized marketplaces such as auctions. The longer term objective of this project is to contribute towards developing the corresponding design principles for decentralized markets, along with a growing literature on decentralized trading, which has been particularly active in the past decade and a half. I mean, Mihai is also here. So the design question is really the one that keeps us up at night. But we started with a couple of two more modest questions, which in a sense come logically prior. What are the equilibrium effects in decentralized markets, which have no centralized market counterparts? And if it were feasible to centralize all of the trading, when would it actually be efficient? And so the first filter theorem will not give us the answer in markets with large traders. Speaking of which, relative to many of the papers in literature, certainly not all papers, allowing, not assuming, but allowing for imperfectly competitive behavior is going to be the main characteristic of markets that we would like to take seriously. In practice, dealing with a strategic behavior with traders' pricing impact is often the key motivation to set up an alternative exchange or to introduce a new financial product. So the fact that traders are non-negligible in the market might matter for why trading isn't centralized, even if centralizing all the trading were efficient, if feasible. All right. To identify the potential welfare benefits from market fragmentation, ideally, we would like to write down a model which can directly nest the standard centralized market model for divisible assets based on the canonical uniform price double auction in which traders submit price contingent demand and supply schedules. Just like in the competitive model, say general equilibrium model, which is based on a uniform price, and its imperfectly competitive game theoretic counterpart games in demand and supply functions. Well, a lot is happening in this literature right now, but still, most of what we understand about imperfectly competitive trading in the supply functions framework has been established in a variant of a quadratic Gaussian setting, which we'll also assume. So all agents utilities are quadratic, all random variables are jointly normally distributed. You'll see that this is not critical to the types of conclusions I'll emphasize. All right, so let's dive in. The description of preferences in assets is standard agents with quasi-linear and quadratic In the quantity traded QI utility, trade multiple divisible risky assets with a covariance matrix sigma. Traders derive utilities from the post-trade allocation, which is the sum of the initial units they hold. I'll call these endowments QI0, and trade QI. These endowments are traded private information. I know how many units I hold. I do not know the position of others, and are independent private or correlated private. So fundamentally, the gains from trade come from the need for diversification or risk sharing. These endowments are heterogeneous. Okay, so that's all completely standard. The sole assumption of the centralized market model we intend to relax is that trading is centralized. It is useful to consider carefully what exactly the centralized market assumption entails. Okay, so let's try to think for a moment. What do we assume when we take an off-the-shelf model of centralized trading? Well, the essence of centralized trading in the standard model is not centralized or decentralized implementation, but rather that there is a single market clearing for all traders and all assets. In particular, two assumptions are implicit in the centralized market assumption. One is that trader participation in the market is complete in the following sense. Each trader trades all assets with all other investors. Okay, so naturally, this assumption has been relaxed by a large literature on decentralized trading based on random graphs, fixed graphs, or more generally, models with limited participation. There is one other assumption implicit in the centralized market assumption. So when trading is decentralized, we need to be explicit. We as modelers need to be explicit, or a market designer needs to be explicit, or a trading protocol needs to be explicit about the types of demand schedules allowed. Right, so imagine I participate in the market with two exchanges, each for one asset, let's say the same asset. Should the demand I'm submitting in one exchange allow me to condition on the price from the other exchange? Okay, so in other words, should I be submitting a fully contingent schedule, R2 to R2, with the quality of each asset being a function of the price vector? Or I should be submitting two uncontingent schedules, R to R, with the quantity of each asset being a function of the price of that asset alone. The standard competitive and imperfectly competitive model of financial markets assumes fully contingent schedules, which in practice correspond to cross-asset conditioning possibilities that are available in some, but not too many trading protocols. More typically, an order placed for one asset cannot be made contingent on prices of other assets. If available, such cross-asset conditioning applies to a limited subset of assets. So feasibility might provide one rationale for why contingent orders are not prevalent. In this project, we show that contingent orders are at least weakly suboptimal. Okay, so let's dive in a bit. Let's try to take a closer look at how cross-asset conditioning matters. So I'm going to be working with a market with I traders and K assets from the previous slide, described by K exchanges, each for one asset, at least in the beginning of the talk. All traders participate in all exchanges. So the participation in the market is complete. All traders trade all assets. But now they submit on contingent schedules. Okay, so what is the significance of that? Well, the assumption of fully contingent schedules in the standard model requires that all assets clear jointly to even determine the vector of market clearing prices and trades. The assumption of fully contingent schedules implies joint market clearing. So apart from the identification of decentralized market effects, which have no centralized market counterpart, the more specific objective here is to understand the welfare and design implications of independence in market clearing across venues or across trading protocols within a platform. Both can be accommodated. That's really what the notion of an exchange represents in a model. Independence in market clearing. Right, so that's the market structure, at least for now. How is the market organized? Well, in each exchange, trade takes place through the standard uniform price double auction, in which traders submit price contingent demand schedules. So these schedules are still contingent on the prices of the assets traded within an exchange. The market clearing price is determined by the aggregate net demand equal to 0, and individual quantities are given by the submitted schedules at the market clearing price. We'll focus on equilibria in linear demands. And all traders are strategic, so nothing I'll say relies on the presence of noise traders or not fully optimizing agents. All right, let's briefly review the centralized market model with large traders and some of its key properties which we show do not hold in other designs. Okay, now let's suppose that there is a single exchange for all traders in all assets, and traders submit contingent schedules. I'll work with net demand so that we don't have to talk about bias and status separately. In games in which traders submit price contingent demand schedules, it is useful to take the perspective of a single trader optimizing against a residual market represented by his residual supply function. This motivates a point-wise optimization problem, which one can show is equivalent to optimization in demand schedules. Okay. In the point-wise problem, equilibrium can be characterized through two simple conditions. The first order condition, which applies point-wise with respect to the price vector, where lambda I is a trader's price impact. With K assets, it is a K by K matrix. Its element KL represents the price change of asset L following a unilateral demand change for asset K. If I knew my price impact, I could compute my best response schedule given that I know my marginal utility. But these price impacts are endogenous. So the second equilibrium condition requires precisely that the price impact assumed by a trader in his point-wise optimization must be correct. That is, it must match the slope of the actual residual inverse supply defined by aggregation of demands submitted by others. Okay, so aggregating other traders' demands and computing the Jacobian, we have that the price impact matrix is the harmonic mean of inverse demand slopes. Okay, the harmonic mean appears from aggregation. These two conditions, optimization, given price impact, and the requirement that the price impact should be correct, give an equivalent characterization of Bayes-Nash equilibria in games in demand and supply functions. Working directly with price impact is not only going to be more tractable, you'll see it in a moment, but it will also provide us with insights about the role of imperfect competitive behavior. All right, two remarks. As the number of traders grows large and price impacts tend to 0, so long as the risk aversion does not increase too fast, in the limit traders submit their competitive demands, which given the quasi-linearity coincide with their primitive marginal utility. For any finite number of traders, my residual supply is not perfectly elastic. In response to my price impact, I reduce my demands. For any given trade, price, I trade less. And second, the equilibrium condition for price impacts is a fixed point in price impact matrices across traders. When trading is centralized, this fixed point can be solved in closed form, and the solution, which I put here in red, reveals a property that turns out to have important implications for how centralized markets function. When trading is centralized, the price impact matrix of every trader is proportional to the fundamental covariance matrix. This proportionality coefficient, beta I, can be characterized as a function of the primitives. I didn't put it on the slide. The point here is that the price impact derives from the concavity of the payoffs of a trader's residual market. So just like in a competitive model, there is a link between concavity and behavior. And when the payoffs are quasi-linear, this link is quite particular, it is linear. All right, so let's keep that in mind going forward. And for the same traders and assets, Let's now consider a multi-venue design. Okay, so consider an individual optimization problem of a trader in a market with K exchanges, each for one asset. His objective function is the same, and so is his information set, the privately known endowment vector. What changes is the choice variable. Now the demand for each asset is contingent on and hence measurable with the price of that asset alone. Okay, so now there is an analogous point-wise version of the optimization problem, but now point-wise only with respect to price PK. Independent market clearing affects traders' first order conditions in two ways. First, now the cross-asset price impact becomes zero just by the definition of uncontingent schedules. Okay, so in contrast to the centralized market, where price impact of every trader is proportional to the fundamental covariance matrix, the price impacts of all traders are now diagonal. So even though the cross-asset price impact is eliminated, the equilibrium outcome, the prices and trades, will not be independent across exchanges, in which case the market would operate de facto as a collection of independent venues. This is the case as long as the payoff itself is not separable, as long as the Hessian is not separable, which will be the case if the payoffs were independent. The second difference with the contingent market is that traders' demands cannot condition on the actual realized trades of other assets, but they still depend on expected trades. Again, as long as the Hessian is not separable, in which case the sigma K elements will be equal to zero, and the quantity traded of other assets would not affect my marginal utility for asset K. Equilibrium will not be exposed. And this makes the problem more challenging. So one can still describe equilibrium through the familiar conditions, optimization, given the residual supply and the requirement that the residual supply should be correct. But now, the price impact of a trader is no longer a sufficient statistic for the residual market. The distribution matters as well. And moreover, there is an additional fixed point between expected trades across assets and traders' price impacts. So I decided that I will talk more about design and the solution method today, but let me still make a couple of remarks. This is an interesting problem. So in fact, because a demand schedule is essentially a contract which specifies quantities demanded as a function of price realizations, we are essentially solving a bargaining or contracting problem with externalities across traders and assets. Okay, so a methodological contribution of this paper is the characterization of Bayesian-Nash equilibria in a class of games in contracts, and contingent contracts, or contingent contracts, and as you'll see later, any contracts in between, without relying on the Nash-Nash counterfactual or restricting beliefs of equilibrium. So, just to describe the solution method in one sentence, we show that the equilibrium fixed point in demand schedules is equivalent to a fixed point in price impact matrices once it's written in matrix form. That is, we endogenize all of the demand coefficients, including the conditional expectations, as functions of price impact itself. This not only makes the problem fantastically tractable, but it will also allow us to understand the implications of independence in market clearing through the structure of the endogenous price impact matrix itself. And the key observation here is that independent market clearing savors the link between fundamental risk, the covariance matrix, and traders' incentives, price impact, in two ways. Well, first, again, the cross-exchange price impact is eliminated. And second, the price impacts within the venues also generally differ from their contingent market counterparts. Okay, so we have a comparative static result. But let me just mention one bit that I need to return to the welfare question. So in two-asset markets, the price impacts within venues always increase due to the inference effect across assets. More generally, the price impacts can be higher or lower compared to the contingent market. So depending on the substitutabilities and complementarities in the covariance matrix, the net inference effect can be of either side. All right, back to the main question. Why might we expect a market with multiple trading venues, which clear independently, to be more efficient than a single exchange which clears all assets jointly? If the market were competitive, the contingent design would be weakly most efficient because it would eliminate the information loss across assets. Okay, so the key is that independent market clearing can lower the trading costs associated with price impact and increase welfare despite the information loss. Well, that's where the possibility comes from. But still, is the contingent design going to be generally inefficient in imperfectly competitive markets? And what exactly can we say, given that the comparative statics for price impact on the previous slide establishes that the price impact within the exchanges can be higher or lower compared to the contingent market? And moreover, the fact that the cross-exchange price impact is eliminated may or may not be conducive to efficiency. Okay, so for a quick example, let's take a look at a market with two assets and a positive covariance. So these are payoff substitutes. A positive correlation. When trading is centralized, the price impact matrix is proportional to the fundamental covariance matrix. So the cross-asset price impact inherits the sign from the covariance. It is positive in the example. Okay, so for traders who are interested in taking the same position for both assets, the cross-asset price impact increases the trading costs. In the same example, a negative covariance and hence a negative price impact lowers the trading costs. But the point is that these effects are absent with uncontingent trading. So even just letting assets clear independently can increase welfare in certain trading environments, which can be characterized through joint conditions on the primitives. A more subtle point, and perhaps the main point of this paper, of this project, is that if designed in the right way, markets with multiple trading venues can be at least as efficient as the centralized market for all traders and all assets. Okay, so this possibility has to do with innovating new assets and separately in creating new exchanges for the traded assets, so essentially innovation trading technology. There is more, but the broader point here is that once we dispense with the assumption that all assets must clear jointly, several instruments in financial market design become available, which can improve efficiency and which would either be neutral or have no counterparts with centralized trading. Okay, so we investigate these different instruments in separate papers. I'll try to summarize the main points, but first, let's extend the uncontingent model in two ways to accommodate modular market structures and various types of innovation. Okay, so first, let's allow for arbitrary restrictions on demand conditioning between contingent and uncontingent. Okay, so now the demand for each asset can be a function of any subset of prices. This allows multiple assets per exchange. In addition, let's allow an asset to be traded in multiple venues. So the market is described by a collection of exchanges, each defined by a subset of assets traded. Traders' demands condition on the prices of the assets traded within an exchange, and they are still uncontingent across exchanges. So the market clears exchange by exchange, and not necessarily asset by asset. The method to characterize equilibrium as a fixed point in price impact matrices carries over to these more general market structures. Now price impacts are block diagonal matrices. All right, so here's an example which motivates the study of all these different types of innovations. Suppose that a new venue for a subset of the traded assets is created to operate along with the existing venues. When will we expect an innovation of this sort to not be neutral to the payoffs of the traders? Well, not in a competitive market with contingent demands. So that's the classical result. Introducing assets in the span of the existing assets is redundant. It does not change equilibrium utilities. In practice, other than for tax-related purposes, new venues or new financial products are used for information-related reasons. So we could say because of some form of market incompleteness, or to lower price impact, to increase liquidity. So let's suppose that the market is imperfectly competitive. Essentially, there is a finite number of traders, and demands are still contingent. Will the spanning results continue to hold? The quickest way to see it is to look at the first set of conditions from the contingent market we set up earlier, where subscript plus denotes the payoff distribution following the introduction of the new venue, collecting terms with trade on the left-hand side, and using, once again, that when trading is centralized, the price impact is proportional to the fundamental covariance matrix. We see that there is a continuum of solutions, which is singular after we introduce the new venue. We see that there is a continuum of solutions, including zero trade. So even if the new venue produces non-zero trades, it will not change the traders' payoffs. So we see that even if the market is imperfectly competitive, even if traders have price impact, the new venue would not be used for informational or liquidity reasons. Once we acknowledge that it is not the case that all assets clear jointly, the spanning results no longer hold. So in particular, there are non-redundant innovations, and if introduced in the right way, they can increase welfare. This is another consequence of the lack of the proportionality between fundamental risk and price impact with independent clearing. All right, so let me observe that apart from new venues, the lack of spanning motivates other types of innovations, which include linking the existing trading protocols by merging their assets, and an inclusion of a new asset in a trading protocol where it was previously not available. Okay, so think of asset listings. I'll present three observations about innovation. Okay, so first, should we expect innovation to be non-redundant in many trading environments, or such trading environments are pretty special? We show as a corollary of a result, which I'll present later, but it is intuitive enough to be stated here, that in the uncontingent market, all innovations are redundant if and only if the payoffs of all assets are either perfectly correlated, in which case the inference is perfect, or independent, in which case the inference is not payoff relevant. And so then innovations won't change the equilibrium price distribution, traders' inference, and price impact. Well, with that, we can ask, what's the scope for introducing new venues? Could we perhaps put a number on it? Well, the intuition behind the general result can be seen in a simple example. Let's consider a market with 3 venues, each for a pair of assets. Even though this market structure is comprised of multiple exchanges, none of which contains all assets, the equilibrium outcome, so price and trades from the contingent market, is also an equilibrium here. Okay, so we cannot compare the schedules directly for the same reason why price impacts are generally not going to be useful to compare payoffs across arbitrary market structures. They are defined on different exchanges, they can have different dimensionality, and so on. However, the price impact per unit of an asset traded across the exchanges is going to be useful to compare the payoffs. Okay, so the following observation simplifies and illuminates the analysis of innovation and welfare. Let the per unit price impact matrix be a K by K matrix such that the total equilibrium payoff the total equilibrium trade of each asset across the exchanges is the same as it would be in a single exchange if lambda tilde were the price impact. Okay, so we show the following. First, we can now compare the payoffs across arbitrary market structures through a single exchange counterfactual. And second, we can identify non-redundant innovations with a change in the price impact per unit matrix, intuitively with a change in the relative price impact across assets. Okay, so you might recall that in a competitive model, innovations are non-redundant if they change relative prices. Here we have an imperfectly competitive counterpart. Innovations are non-redundant if they change relative price impacts. Okay, so in this example, the price impact per unit matrix coincides with the price impact from the contingent market. In particular, it is proportional to the fundamental covariance matrix. So intuitively, since the total demand for each asset is a function of the prices of all assets, the cross-asset inference effects in a market with 3 venues exactly mimics the cross-asset price impact from the contingent market. We've just answered the following question. When can markets with multiple venues function as the centralized market? When innovation completes traders' inference this way. Okay, so, even though traders submit demands that are not contingent on the prices of the assets traded in other venues, so no expectations about trades are perfect, equilibrium is exposed. This result also puts a bound on the number of innovations that can be introduced in markets and be still non-redundant. It shows that we can implement the contingent market allocation with simpler schedules. Right? So 2 assets per exchange suffice. In order to implement the contingent market allocation, it must be that for every pair of assets, there is a venue where these assets are cleared jointly. Okay, so the maximal number is k times k minus 1 over 2. What are the implications of all of this for welfare? Well, we've just shown that a design with multiple venues, and none of which contains all assets, can be at least as efficient as the centralized market for all traders and all assets, and can thus bound the payoffs at the corresponding contingent level. It turns out that multi-venue designs can do strictly better. Okay, so not only are the contingent schedules unnecessary, but they can also be suboptimal. Why? Well, we had anticipated a potential trade-off between information loss and price impact. We can now see the trade-off in the indirect welfare function by substituting the equilibrium traits as functions of price impact into the utility function. Okay, so when a design change, when the market structure changes, we can decompose the corresponding change in the equilibrium surplus into a term due to information loss, the price impact of a given asset, so the diagonal element of the price impact per unit matrix, and the price impacts across assets, so the off-diagonal elements of the price impact per unit matrix. So where are the potential welfare gains from multi-venue trading coming from? Well, the price impact of a given asset and the price impacts across assets represent respectively the cost of risk sharing of a given asset and the cost of diversification across assets. Okay, we show the following. As a corollary of the comparative statics of price impact from a few slides back, we show that in 2 asset markets, the contingent design always minimizes the cost of risk sharing, the diagonal elements of the price impact matrix. So for multi-venue trading to increase welfare, the cost of diversification must decrease sufficiently. However, more generally in markets with multiple assets, multi-venue trading can lower the cost of risk sharing, diversification, or both. Which designs are more efficient? In general, neither the contingent nor the contingent design is going to be efficient irrespective of market characteristics. Two observations here. The key primitive is the joint substability of the asset payoffs, the covariance matrix, and trading needs. Well, we can see it by looking at the equilibrium surplus matrix, which is a quadratic form with the matrix coefficient being a function of price impact and hence the covariance. Okay, so we show that even if all assets are complements or substitutes, which design is efficient depends on whether the market is one-sided. Okay, so traders are interested in taking the same position in all assets, as is the case in the market for treasury bills, or some assets are demanded and others are supplied, let's say in dealer markets. More precisely, what matters is the heterogeneity in the joint substability, which can favor market structures intermediate between contingent and uncontingent. Right? So intuitively, then inducing the asymmetries in trading costs can be beneficial. Now, these observations are in sharp contrast to the competitive model, where any innovation that increases demand conditioning also increases welfare, irrespective of market characteristics. All right. So now let's suppose that the innovation in trading technology, so the innovation that links market clearing across assets, is not available. We can still ensure that markets with multiple venues are at least as efficient as the contingent design by letting traders trade assets whose payoffs are defined by linear combinations of the existing assets without altering traders' endowments or the net supply of the assets in the market. Right? So these are derivative products. I think ETFs, ETPs, or proper derivatives, which will be redundant in a contingent model. So in fact, the standard methods for pricing derivatives either assume the existence of a replicating portfolio, that is, they assume that we can price a new product through linear combinations of the prices of the traded assets, that is, they assume that derivatives are redundant, or endow a model with an exogenous demand for the derivative product. But if we want to understand which products are going to be introduced as a function of the underlying characteristics of traders and assets, we would need an equilibrium model of non-redundant derivatives. With innovation defined by payoff bundles, the framework from the previous slide becomes an equilibrium model of non-redundant derivatives. Okay, so once again, we can implement the contingent market allocation now with purely uncontingent demands. So in fact, in a market with two assets, introducing just one derivative, which places non-trivial weights on the payoffs of both assets, will complete inference. And once again, we can do strictly better. In fact, we show that in certain trading environments, one can do strictly better, not only compared to the contingent design, but also relative to the maximal welfare feasible with exchange design. Okay, so this is precisely because of the additional degrees of freedom allowed by derivatives. We can choose the weights with which we bundle the asset payoffs. Likewise, derivatives can do strictly worse than the minimal payoff feasible with exchange design. So this exercise identifies the benefits of some instruments and exposes the risks associated with others. Innovation in trading technology, in introducing new exchanges, gives rise to a lower payoff variance across the trading environments. Okay, so this exercise also shows that innovation in trading technology and new financial products are distinct instruments, and they should be regulated separately. Right, how much time do I have?
Hannah, you have 5 minutes left.
Perfect, perfect. All right, so I've been talking about centralized versus decentralized, but clearly markets have never really been centralized. And these results show that it matters. These results show that the classical results based on spanning and other theorems which rely on them, I mean, spanning is the foundation for asset pricing, do not carry over to trading environments in which not all assets clear jointly. Okay, so there's space to develop new results for pricing, new financial products, innovation in trading technology, new contracts, using game theoretic tools for imperfectly competitive markets. So to make this more precise, the spanning methods provided us with a representation of uncertainty through the implied state space. It was an as-if result, over which this state contingent securities were defined. State contingent pricing is not useful when spanning doesn't hold. Our approach to characterize equilibrium as a fixed point in price impacts allows us to introduce new techniques based on projected price impacts, these per unit price impacts. These techniques can be extended to the comparative analysis of different types of innovation based on projected price impacts of the matrix representations of the corresponding fixed points. And these methods could further be extended to study design problems in static, dynamic, centralized, and decentralized markets, given the progress that has been made on modeling imperfectly competitive trading in the supply functions framework in the past 10 years.